We all grew up knowing plus, minus, times, and divide. In this video, we'll add one more operator to the mix. It's called modulo, or sometimes just mod. We write modulo operations just like addition or any of the others. We write a symbol between two numbers. To write modulo, we use the percent sign. So we would write 11 mod 4 like this. And just like all the other operations, the result of mod is just a new number, in this case the number 3. When A and B are both positive, we can compute the result of mod with this little program. All it does is subtract B from A over and over again until finally A becomes less than B. Whatever value A has left at the end, that's the result of mod. That's all there is to it. It's just this little loop that subtracts B as many times as it can from A. The modulo or mod operator will really find a home when we use it with arrays. That use is so important it has its own video. But for now, let's just play around a little bit with mod to get a feeling for what it does. Let's begin by finding the result of A mod B for a bunch of different values of A and B. So I'll line up values for A in a row, and we'll try out a bunch of different values for B. Let's start by setting B to 3. And now we'll plug in the values of A from this row and compute A mod 3. Starting at 0, we look at the loop. 0 is not greater than 3, so nothing happens, and the value is unchanged. That is, 0 mod 3 is just 0. The same story is true for 1 and for 2. So 1 mod 3 is 1 and 2 mod 3 is 1. Now how about 3? 3 is greater than or equal to 3, so we subtract 3 from A, giving us 0, and that is A mod 3. Using the same logic, 4 mod 3 is 1, and 5 mod 3 is 2. Now we come to 6. Well, looking at the loop, 6 is greater than or equal to 3, so we subtract 3 from A, leaving us with 3. And that's still greater than or equal to 3, so we subtract 3 again, leaving us with 0. So 6 mod 3 is 0. And I'm sure you see the pattern. A mod 3 gives us a never-ending repeating cycle of the numbers 0, 1, and 2. We can even group them together visually like this. Now let's try A mod 5. Well, we just apply the loop at the top for different values of A, and we find that from 0 to 4, the result of A mod 5 is just 0 through 4. How about when A reaches 5? Then A is greater than or equal to 5, so we subtract 5, giving us 0, and the pattern starts again. When B is 8, the pattern is now 8 elements long, containing the numbers 0 through 7. In general, as A goes up and up, for any B, we will get back a never-ending sequence of the numbers 0 through B minus 1. If you imagine that A is something like frame count, then we can use mod to create a pattern that changes over time. Here's an example where I'm creating values of X running from the left to the right, and I'm using mod to get the Y value. And for now, just for convenience, let's pretend Y goes up. You can see that the Y values go up and up for a while, and then they drop back to 0, only to climb up again. By changing the value of B, I can make the cycle as long or as short as I like, and it just repeats over and over. Just by changing the geometry, I can make lots of different patterns using the mod operator. And they're all kind of interesting and fun to look at. Another way to think about modulo is like a wheel of fortune. To compute A mod B, we break the wheel up into B slices, and then we spin it so that the slices pass under the pointer at the top. In this example, I want to find the value in the upper left. I want to discover what is the value of 10 mod 6. So I break the wheel up into 6 pieces, and then I spin it. And I spin it so that the wedges pass under the pointer 10 times. So I'm passing through 10 of the wedges. And you can see in the upper right, I'm counting the wedges as they pass by. Here's the 9th wedge, and here's the 10th one. The 10th wedge stopped at 4, and the result of 10 mod 6 is 4. Just for fun, let's try something smaller. How about 10 mod 3? We can predict that this will be 1 because we're going to subtract 3 3 times. So that means we'll subtract 9, and that leaves us with 1. But we can watch the pieces pass under the pointer, and now we're on the 10th piece, and sure enough, we're pointing at 1. Let's try a much larger number. So now we're going to try 8 mod 22. Well, A is less than B here. 8 is less than 22, so we're never even going to make it all the way around. But let's go ahead and spin it. We'll count up 8 slices, and the result of 8 mod 22 is just 8. So let's make our target number much bigger. Let's predict what we're going to get. We can subtract 22 from 51 twice. That takes out 44. That leaves us with 7. So we expect the result of this will be 7. Let's run the wheel and see what happens. We're counting up on the right. And I can even make this go a little faster so we don't have to sit and watch it all. I'll slow it down when we get close to the end. All right, we'll slow down a little bit. And sure enough, 51 mod 22 is 7. How about negative numbers? I wrote this little sketch to help us visualize mod for different values of A and B. The horizontal axis has different values of A. So here, A is running from -8 to 8. And as you can see at the top, I'm going to find the value of A mod 3. So B is 3. Let's draw this. Here they are. I'm putting a circle at each integer value, but mod is happy to take floats, and it's generating all the numbers in between. So we can see, starting at 0 and working our way right, we get the values 0, 1, 2, 0, 1, 2, and so forth. And working our way negative, we get 0, -1, -2, 0, -1, -2, and so on. If I increase the value of B, I just increase the length of the cycle. Now I'm computing A mod 4, and so we get the values 0 through 3. A mod 5, and so forth, just makes the cycle bigger. Now what if we use negative numbers? Well, let's work our way back down. A mod 4, A mod 3, A mod 2, and now A mod 1 always has the value 0, because you can always subtract a number from itself. A mod 0 really doesn't have a meaning. If you try to compute this, processing will give you back a special code, meaning this isn't even a number. Well, let's make B negative. The value of A mod -1 is always 0, and if we keep making B negative, we find that we get back the very same pattern that we had when B was positive. So whether B is positive or negative doesn't really matter. What matters is the value of B. In this case, the value is 5. Now I mentioned that B can be a fractional number as well. So let's turn off the dots. And now I'm going to draw just random dots. I'm going to pick a random number from -8 to 8 for A and plot the value of A mod -5. So here we are, and we're going to get the very same graph that we just saw. It may look a little different because A mod 4 still has the value 4, but A mod 4.5 has the value 4.5 all the way up to 4.999. When A finally hits 5, the pattern goes back to 0. Let's make B positive. And here's A mod 4, where I'm picking random values of A from -8 to 8. What if B is a fractional value? Well, let's nudge B down. Let's find A mod 3.5. And we get back exactly what we expect. This is a cycle that repeats every 3.5 units. Now, if we draw just the integer values of this, it can look a little bit weird. It looks like the cycle is getting longer and shorter and longer and shorter, and that's just because of where the integers happen to fall. If you pick a really wacky value for B, say 3.1714, just making up random digits, then you'll get back cycles that seem to randomly jump around between the two values that surround the fraction, in this case 3 and 4. And if that's what you're looking for in your sketch, that's a great way to make those cycles. In part 2, we'll look at a couple of examples of using mod in everyday life.